let's start by taking questions. So you guys should have completed the chapter 1 homeworks and the chapter 1 review. I did post a key with the review, but if there's questions on things that you want to ask about, as I kind of checked through your guys' homeworks here yesterday, I noticed that there seemed to be things that you were unsure about on there, so I want to make sure that we take some time here in class and give you the opportunity to ask specific or individual questions about anything you might have encountered, either from the homeworks or the reviews, so that I can provide any kind of clarification that you need before we're taking the test. Okay? So whenever you are ready, go ahead and raise your hand or whatever, and we'll kind of take those one at a time. Okay? Again, it can be super specific, like an individual problem. It can be something more broad. It doesn't really matter. This is a time for us to kind of clear things up that might not be totally clear. Josh? Yeah. So I think there's two 1.8As, because there's a number, it became a lettering issue. Do you mean the first A or the second A? So this one? Yeah. Okay. Okay. So the first thing I'm going to do is I'm going to translate what's going on in this sentence into values for A, B, H, and K. Okay? So a reflection across the x-axis tells me that A is negative. Translating 3 units to the right tells me that H is -3. I'm not told anything about a shift up or down, so that tells me that K is 0. Oh, sorry. Yeah. I'm not told anything about any horizontal stretches or shrinks, so it tells me the magnitude of B is 1. I'm not told anything about a vertical stretch or shrink, so it tells me the magnitude of A is 1. And I'm not told about a reflection across the y-axis, so that's telling me that the B is positive. So concluding here, I can say that A then must be -1, H is 3, B is 1, and K is 0. Are you okay with how I've come up with that? Okay. So what I'm going to do then is I'm going to take my general transformation, that g of x is equal to a times f of 1 over b times x minus h plus k. And I'm going to fill in my values now. So I have -1 times f of 1 over 1 x minus 3 plus 0. Okay with that? Okay? If I simplify this down, this is just negative f of x minus 3. Okay, there. Okay. So now I'm going to go ahead and do that, because I know what f of x is. It's defined as x squared plus 3x. So I'm going to have then -1 times the quantity x minus 3 squared plus 3 times x minus 3. Okay with that? So I evaluated this. So what I did is I plugged in x minus 3 into f of x. So that's where I get this from. So the -1 times the whole thing. That's what that means when we have something inside, like that function notation. That's what that means, right? Like if I did f of 3, I'd put a 3 everywhere there was an x, right? If I have x minus 3, I'm just going to put x minus 3 everywhere where I have an x. Yeah, well, we still have to keep going because we still have more to do here, but so I have -1 times, let's see, x squared minus 6x plus 9 plus 3x minus 9. And then if I combine like terms and distribute the negative, what do we have? X squared, or negative x squared plus 3x, and then the 9's cancel out. So this would be your final answer, I think. Anthony? No. So the transformation descriptions were something you had basically every chapter last year in Algebra 3-4. I'm going to consider that prior knowledge. So that's something you should be responsible for, as well as like the general form for a transformation. Again, every chapter in Algebra 3-4, you had some version of this with the given function. So again, going to consider those things prior knowledge. At points in this course, when we're encountering things that I would consider new material, like the first time you're seeing it, we will give you formula sheets in some of those instances, or give you formulas for some of those. But in this case, where the things you're encountering have largely been review from the previous course, my assumption would be that we still have that, or can reacquire it rather easily. But that's a fair question, right? Like, you need to know whether you need to spend some time reacquainting yourself with those things if they've kind of drifted on you. So again, perfectly reasonable thing to ask. Kristen. Sure. So we're looking at the homework, right? Okay. Okay, so 50, and you just cared about part E. So this one is a little bit challenging algebraically on what to do. Just as a reminder here, the goal is I want to start by isolating the x variable, so getting one x all by itself, and then I'm going to swap the x and y variables. And that's basically all I need to do to find my inverse. The trick here is that I have x's in two locations, and one of them's in the numerator and the other's in the denominator. So it's maybe a little unclear at first glance what to do. The first thing I would do is get rid of the fraction. So the easiest way when you have a ratio like this, where one fraction is equal to another, is to cross multiply. Remember, cross multiply is a solving technique, not a way we multiply fractions. So when I do that, I get -7x minus 23 is equal to y times the quantity, x plus 3. And then I'm going to distribute that y through. And I'm going to move all the x's onto the left-hand side. So I'm going to subtract xy from both sides. And at the same time, I'm going to add 23 to both sides, so that I have only things with x's on the left side. Now, because I have only x's on the left-hand, or only things with x's on the left-hand side, I can factor. So there's a greatest common factor of x in each of them, so I can take that out. And then I can divide both sides by the -7 minus y. And that's what I needed. So the last step is just to switch out the names of my variables. And that should do it. Does that make sense, Kristen? Yeah. Again, not a trivial thing to do, right? There was some tricky algebra involved there, in particular, like doing the cross multiplying and then doing that greatest common factor maybe was not obvious if you haven't seen that trick done before. But now you have, right? So it goes into the toolbox of tricky things you can try to use. Often when you have a situation where you have variable in both the numerator and denominator that you're trying to solve for, that's going to be a useful tool. Haley. Sure. Three. That. So we're talking about this one right here, right? Okay. It says identify any discontinuity in the function and help and determine the type of the discontinuity. So I'm going to do this algebraically. So I'm going to start by factoring. So I notice in the denominator, I can factor out a greatest common factor of x. And then in addition, the x squared minus 4 is a difference of two squares. So I know that can factor to x plus 2 and x minus 2. And then I notice there's a bit of reducing that I can do. Which reduces down to this. Are you cool so far, Haley? Okay. So remembering from last year, when I have a rational function, I reduce out a factor completely from the denominator, like we did here. This causes a removable discontinuity. So I take the factor that I crossed out, set equal to 0. So I have a removable discontinuity, x equals -2. Okay with that? Okay. The other thing that I remember from last year is that in a rational function, the denominator set equal to 0 gives me vertical asymptotes. And a vertical asymptote is the same as an infinite discontinuity, right? When we described what an infinite discontinuity was, that was really the same thing as a vertical asymptote. Well, let me rephrase. A vertical asymptote is a type of infinite discontinuity. They're not exactly the same thing. Is that still okay, though? Okay. So when I set this equal to each of these parts equal to 0 and solve, I have x equals 0 as an infinite discontinuity, and also x equals 2.
So is that only removable if you reduce it?
Yes. That's the only way to generate a removable discontinuity that we've seen to this point. There's a jump discontinuity, but you have not talked about a situation where you would get one of those. I gave you, like in the notes or whatever, we described one, but you haven't spent any time talking about like piecewise functions in any course prior to this one. And me talking about it for like, I don't know, a minute and a half in notes one day, I don't think makes a reasonable test question to make out of that. So again, fair thing to ask about for sure. The only situation where I would think it would be reasonable to ask you about that is I give you the actual picture of the graph, where all you have to do is look at it and be like, oh, this spot has a jump discontinuity because I can see with my eyes. I didn't have to do any algebra to generate that. That I think would be reasonable, but asking you to do something algebraically with like a piecewise function, no. We're not ready to do that. Or is it unreasonable? Maybe you are, but it's unreasonable for me to ask you guys to do that based on what we've done together in this course, right? and what you've done prior in your previous math courses. So hopefully that seems reasonable, right? And again, absolutely fair kind of thing to ask if you're like, do we really need to worry about this for a test purposes? And if it's something we've barely talked about, probably the answer is no. All right. Others, who else? Questions from this? We can do this as kind of as long as you need to today. This is mostly what I have today budgeted as. So if you have things that you're confused about still, or things that you did on the review and you weren't sure about, this is a great time to kind of clean some of this stuff up. Abigail. Okay. Let me look at 1.7. Okay, so these guys here. Okay. All right. Is there one in particular you want to talk about, or? Okay. So since Abby is good with any of these, does anybody here have one in particular on 1.7 that they want to talk about, so we can kind of double, kill two birds with one stone, proverbially speaking? Nobody's getting killed here. Kristen? D. Sure. So the trickiest one, or the trickiest situation here, Abigail, is dealing with the composition. But it's not that bad. So we'll just kind of take this as it goes. The ones where you're just having addition or subtraction or multiplication or whatever is typically much easier to deal with. The composition is a little bit trickier, but not so bad even in this situation. Okay. So this is the same thing as f of g of 4. And one way you could attack this would be to compute g of 4 right now and just leave whatever that number is in for f. And then you can compute the value for f. But since we want the domain, I'm not going to do it that way. I'm going to do the composition first and then plug the 4 in after I've done the composition, rather than plugging the 4 in before I do the composition, so to speak. Just because I want the domain, and it makes it a little bit easier if I can see the functions involved beforehand. Okay? So this is the same thing as f of the square root of x. So that's 1 over the square root of x, and then minus 1. Okay, here. All right. So I'm going to pause here and look at this, and then we'll plug the 4 in after and get the actual number. Well, I guess we can do that right now. So if I do that, I get just 1. But this is the part that I'm going to look at to do the domain. So when I'm thinking about a domain, and all I'm given is an equation, what I want to think about is, how can this equation become undefined? So when I look at this particular equation, there's 2 parts that I would be concerned with. I know that a square root can cause something to be undefined, right? When is a square root going to be undefined? When it's negative, right? So I know that the stuff underneath the square root must be non-negative, greater than or equal to 0. So I'm going to take the x that's underneath the square root and set it greater than or equal to 0. The other place where this function could be undefined is when the denominator is equal to 0. So I'll set that not equal to 0. Okay with that so far, Abigail? Okay, so I'll just now solve for x. I'll add 1 to both sides and then square both sides. So my domain is both of these two things. Now to translate this into a single like interval or whatever, which is probably what you'd want to do, although I guess here it doesn't describe like what form you want your domain in. Let's write it as an interval. Is that okay with you? Okay. Probably the easiest way to think about this is to just kind of draw both of these two inequalities on a number line and see the overlap. So let's say the first inequality, greater than or equal to 0, I'll draw here in blue. And the second inequality, the x not equal to 1, I'll draw here in green. Okay with how I've drawn those two inequalities? Okay. So the overlap that I see happens here and then there. You guys kind of see that? And you don't really need to draw the number line to do this, but I think it's a helpful visualization for you. Like if you're not sure, like, how am I going to kind of take this not equals to thing and then this inequality and like combine them together and get like an interval out of this? I think that helps. So this first piece is 0 to 1. Notice that the 0 has a bracket because both parts on the number line include the 0, but one of them doesn't include the 1. So 1 isn't in both of them. And then the other part starts at 1 and goes on forever. So I'll have 1 to positive infinity. And again, both of those get parentheses because, again, 1 isn't included in the green line, so it can't be in both. So this would be the domain. Okay with that? Little bit of work there to get to that. And again, you don't need to do it the number line. I think it's a helpful way to visualize it if you're having trouble, like, how do I take these two things and like find the union of these two sets? Seeing it is often easier than like just thinking about it in your head. So that's why I like to kind of think about it as a number line situation like that. Jason. Sure. So f in the same section. So we're doing f of -2. So let's do f of x, and then we'll plug in the -2 at the end, because again, I want to see the composition to do the domain. So that's going to be f of 1 over x minus 1. And when I do that composition, I'll have 1 over x minus 1 minus 1. Now, we had a name for this last year in Algebra 3-4. Do you remember what this situation was called? It's called a complex fraction. And there's a couple of different ways to simplify this to make it a little bit easier to deal with, because this idea of having a fraction inside of another fraction is not very convenient, and it's going to make finding the domain a little bit difficult if we leave it in this form. So, well, I guess it will be fine. We can leave it in this form. I'll show you how to simplify it also, but it's actually won't be that bad to just kind of leave it the way it is to find the domain. So on second thought, let's just deal with it. Okay, so I see two separate places where I have a denominator, right? I see this part right here is a denominator. And then I see this part right here that's a denominator. Is everybody okay there? So the first one, it's easy enough to solve and get just x can't equal 1. This one, I will add the 1 to both sides, and then I'll cross multiply, and then I'll add the 1 to both sides. I got that. Is everybody okay there? Jason, you're still okay? Okay. And then so to do the domain then, I'll just graph both of these on the same number line. So x not equal to 1 looks like this. And x not equal to 2 looks like this. So I have 3 places where I have overlap. So my domain would be negative infinity to 1, union, 1 to 2, union, 2 to positive infinity. Is that okay? And then our last step would be we have to go back and plug negative 2 into this. So if I do that, I have 1 over negative 3 minus 1, which is the same thing as 1 over negative 4/3, which is negative 3/4. Okay with that? We'll skip talking about simplifying a complex fraction for right now, since I don't know that it was really going to be actually helpful in dealing with what we had to deal with here. I think it was just as easy to leave it the way it was. To get since we're just getting a number out of this anyways. Okay there? Josh. 48 from the homework. Yes. Okay. Do we need to do like the whole 48, or are we just looking for, I mean, there's A, B, C, D, and E for this. Okay. So determining if the function is 1-to-1, probably the easiest way to do that is to just look at the graph. But I really don't even need to do that. I mean, I know what the graph is going to look like. Since this is a rational function, or in fact, it's a simple rational function, I can see the vertical asymptote should be at -4, and the horizontal asymptote at -9. So it's just going to look kind of like this. Now you'll see the same picture if you type it into your calculator, and you could certainly have done that. I think it was quicker for me just to draw a little picture than to get the calculator app up and then put the thing in and mess with the window to get a good window and do all that jazz if I knew what it was going to look like. So what I'm looking at for the graph is I'm just looking to see if it passes a horizontal line test. That's probably going to be the easiest way to tell if something is 1-to-1 if you're given like a function written as an equation like this. So here, is there any horizontal line I can draw that intersects this graph more than once? No. So it is 1-to-1. So this passes the HLT. So it is 1-to-1. D, it says predict if the inverse relation is a function or not. Well, because the function is 1-to-1, that tells me the inverse is a function. Now, technically, our function should be bijective, but the onto part when you're given an equation is just kind of taken as a given. So we don't really have to worry about that, because when we describe our function as just an equation like that, we assume that the range is just whatever the range is for the function. So it's automatic. Like the onto-ness is kind of given. So you don't really ever have to check that if it's given to you as an equation. You can just assume it's onto.
So whenever you have a one-to-one graph,
Correct. Yes. And then part E is similar to what we did with Kristen, but this one's a little bit different because it's not a proportion. So it's certainly worth doing again. So again, the idea here is we're just going to try to get the x by itself and then swap the x and y names. So I'm going to start by adding 9 to both sides. That gives me this. And then I'm going to cross multiply. And then I have to FOIL. And I'm going to move everything that doesn't have an x in it to the other side. Oops. So I have negative 33 minus 9y. Oops, that's a 4y though, I think. So far, so good, Josh? Yeah, that's a 4. It's 4y and 9x. It's unfortunate that I picked 4s and 9s to be in the same problem given my penmanship issues, but so now I'll factor greatest common factor of x from the right-hand side and then divide both sides by y plus 9. And then we'll just swap the x's and y's. So very similar pattern to what we saw with Kristen's question, right? Where at some point we need to cross multiply, move things around, do a greatest common factor to pull the x off, and then divide both sides by all that leftover junk after the factoring. Now this one I think was a little bit trickier because you also had that FOIL in there or whatever, but not much trickier, like marginally. Like when you have the FOIL, like the two parentheses next to each other, I'd expect that you think, oh, better FOIL this out. Oh boy, I'm a dummy. We could have done that much easier. Just as an aside, at this step, I guess I could have just divided both sides by y plus 9 and then subtracted the 4. And there's the x by itself that way also. Yeah, so if I made a common denominator, where I did like y plus 9 multiplied to the top and bottom, that's 4y plus 36, but the negative distributes, which gives me exactly negative 33 minus 4y over y plus 9. And then when I swap the x's and y's, I have the exact same thing. So they are the same result. So whether you went this way or this way, either is okay. I don't remember what answer I put in the answer key. Do you guys remember which one was there? Oh, it was an even. Okay, fair enough. But either one of those answers are perfectly acceptable. And on a test setting, I would accept either answer with no prejudice there. So, okay, who's next? Haley.
On the review on 1.5, could you do letter D?
Sure. Let me check real quick to see if I have 1.5 on here. I don't think I did, though. No. Okay. This is the odd even ones. Cool. So just as a aside, to show something as odd, we need this, and to show something as even, we need to show that. Either way, what we need to evaluate is f of negative x. So that's what I'm going to start with. So far, so good. So that's going to give me just negative 2x squared over negative 3x cubed minus 4x. Well, that's definitely not what I started with. So I know it's not even because that's not f of x. Let's check to see if it's odd. So I notice the denominator, or the numerator, I should say, is the same. So I'm going to worry about the denominator. If I look at the denominator, I can try to factor a negative 1 out of there. I notice that this is now the same. So what this means is really I can take like 1 over negative 1. Out of that, right? And that's the same thing then as negative 1 times f of x. So we would say that this is odd. Jason? So negative x squared is x squared, and then times negative 2 is negative x squared. There might have been an error on the answer key on this one. I think that there was, somebody asked me, I think, about this after class one day. This one might have had a mistake on the answer key. But I think that, I'm quite certain that what we did here was correct. As an aside, talking about this odd-even part, you guys remember that how we said if we had a polynomial, or really like the sum or difference of two functions, we said that an even function plus another even function is even, and an odd function plus another, or plus or minus, it doesn't really matter, another odd function is odd. But if you had even plus or minus an odd, that was neither. We kind of use that as a shortcut. At least to give you an idea of like what answer should you be searching for when you're actually trying to prove this. And the idea was with the polynomial, if like all the degrees were even, then that function was even. All the degrees are odd, the function is odd. What happens for a fraction? So if I have like one fraction over another fraction, if I look at the plurality of f of x and g of x, can I tell whether we're going to be whether the quotient is odd or even? Well, hopefully it wouldn't be surprising that even over even gives me even. If you have even over odd or odd over even, that's going to come up to be odd. What's maybe a little bit surprising is that odd over odd gives us even. Let's prove this one. That's probably the kind of the surprising result. So let f of x and g of x be odd functions, and h of x is going to equal f of x over g of x. So h of negative x would be f of negative x over g of negative x. Since f of x is odd, I know that f of negative x is just negative f of x. And likewise, g of negative x is just negative g of x, right? And the negative signs are going to cancel. And we're left with our original h of x. Which is our definition for even. So odd over odd should be giving us even. So if I go back and I look at this question that Haley asked us about, I notice that the numerator is an even function because it's just a polynomial where all the degrees are even. And the denominator is an odd function, right? Because it's just a polynomial where all the degrees are odd. So this is even over odd. It should be odd, which is exactly what we found when we did it algebraically. So again, I answered Haley's question, then we did a little bit more. But I think that like looking at those general trends, like is there a way for me to predict what the outcome is going to be, helps, right? If you're getting to the test and you're like, what should this be? And you can tell immediately just by looking at it, like, oh, this should turn out to be an odd function, and your algebra isn't matching up with that, probably gives you some indication that you goofed up a negative sign somewhere along the way. It gives you some, rather than just going, oh, it's neither, it gives you the opportunity to go back and kind of look at it again. You know what I mean? And it's an interesting, like, mathematics question about, like, can we make a prediction that's always true, right? Which is really kind of what mathematics is mostly about. It's not so much computation as it is, like, can I come up with a rule that describes a situation always? And how general can I make the situation and still have my rule hold, right? Like, 1 plus 1 is even. Okay, that's a nice rule, but like it's very specific, and we generalize this to odd plus odd is even. Like that's much, a much better rule. Anyways, that's an aside. Back to you guys' questions. That's enough about me and the stuff I'm interested in. You might have been interested in that stuff too. And it, in a way, it helps. Kristen. Oh, certainly can be. I think if, and I'd have to sit down and really think about it because I'm not sure it's always true. But I think if either the numerator or denominator is neither, the fraction is going to be neither. My question would become if they're both neither, is that going to guarantee that it's also neither? And that's the one that I wouldn't be sure about without having to like sit down and think about it a little bit. So yes, the fraction can be neither. For sure, if one of them is either the numerator or denominator is neither and the other is odd or even, that's still going to come out to be neither. The other is the one, neither over neither is the one that I'd have to sit down and kind of think about. To whether there's like some weird, like kind of degenerate case where it works. My suspicion is it wouldn't, but I don't want to say for sure because there might be one little stupid case that, where I'd be wrong on. I don't want to tell you something that's not true. Or that I don't know for sure. I'd have to sit down and think about it. We could do that right now, but I think you guys have bigger fish to fry than like going and exploring some little question there. Jason.
So for finding either odd function, you take and factor out the negative and either put it over one or put it under one. What is that? How is that outcome going to be?
Okay. So what I'm checking for is whether it's odd or not. So the odd, I need to get a -1 in front of f of x. And that's what I accomplished here when I factored the -1 out from the denominator, is it basically means now I have a -1 in front of my f of x. So that's what I'm checking for there. Does that make more sense? And that's, again, really excellent question. Like if you don't understand algebraically what it is that I'm showing, the proof doesn't make a lot of sense, right? And if there's something in there that, like, okay, you did that, and I see that you did that, and I see that, like, whatever you factored is true, the algebra, there's no issue there, but I don't understand, like, why you did that and, like, what that's showing you. You like to be able to do this well, you really need to understand those things, and, like, that's an important question to ask. If it wasn't clear, we can talk about it a little bit more and try to straighten those out, so it is clear, like, oh, now I see why factoring that thing out made a difference or didn't make a difference or whatever. So, yes, good question. Josh. Yeah, of course. Is this being helpful, guys? Yes. Again, if you need something else, we can certainly do something different, but as I was checking things, it seemed like there were ideas and questions and topics and stuff that seemed like we just needed some time to ask some questions or whatnot, which is totally understandable. Okay. So 30 says to find two functions, f of x and g of x, such that the composition of them is what I've been given. Okay. So in general, when I'm doing this, what I'm going to look for, or what I'm going to remember, is that f composed g of x is really the same thing as just f of g of x. So what I'm going to do is I'm going to look for like an inside function and an outside function. So if I do that, to me it looks like x minus 3 is my inside, because that's a function that's like the inside of what's going on there for h of x. And my outside function appears to be the square root, or the cube root of x. Since that's the part that's like around the whole thing. Does that make sense, Josh?
Yeah.
Okay. There are lots of answers you could have put here. This is not the only unique answer. I think this is the obvious one. There's one answer that works for every one of the problems, no matter how I constructed this. It's the cheat answer, but you could pick g of x to just be x and f of x to be h of x, or vice versa. And that will always be true, which is kind of a cheaty way of doing it, but it didn't violate the directions there. The reason this is true is that x is your identity element for the composition of two functions. So if you compose any function with x, you just get that function back. Just like when you multiply by 1, you just get that number back. Or when you add by 0, you just get that number back. Nothing happens. The same thing, composition with the function, like, you know, with f of x equals x. If you compose anything with that, you just get whatever you composed back again. Doesn't really do anything. So that's a cheaty way of doing it. And that works for every problem like that. You could kind of do that sneakiness. And there's other things you could have done here too, but they're less obvious. These would have been the two I would have expected to see most often. There's other things you could have done though. Is that good enough, Josh?
Yeah, I was like,
Yeah. I mean, most of this stuff, it's just about looking at it the right way. In fact, most of mathematics is like, can I look at it the right way to make this as easy as it possibly can be? Or am I going to like bang my head against the wall for like an hour trying to make things harder than maybe it needs to be? And as you're learning things, like it's not obvious when, like if you're actually banging your head against the wall, or if like there's an easier way to do things. I wish that it would always be like, oh, it was always going to be easy. It's not, and it's okay. Like sometimes it has to be hard until it gets easy, and that's just kind of the way that it works, or that's the way learning works sometimes. So like, don't feel bad if you took a problem and made it like seem like you're making it harder than it needs to be. That's okay. Knowing to stop and ask about it so that you're not just like banging your head against the wall for too long is an important, like knowing kind of when to quit and walk away and take some time and come back to it, or like take some time and talk to somebody else or ask some questions. Like those are important skills to have, and that's good. You know, a little bit of perseverance so that you've like tried some stuff that you don't think is working, or like, did this work? I don't know. I got an answer. Is it the right answer? I'm not really sure anymore. Like, is there a better way to do this than guess and check? Because I got an answer, but I mostly just guessed and checked it. You know, like those are all normal approaches when you're trying to figure out something kind of for the first time through. And that's okay. It's time consuming and maybe frustrating and slow, which I know when you have a lot of classes to deal with and a lot of other things, like you really abhor like having to struggle through something and not make a lot of progress. But I promise, like, you are making progress. It's just not on a sheet of paper. Like, that's an important part of the learning, though. That's enough for my soapbox. But I just wanted to, you know, like, it seemed like people were, you know, you make the comment about overcomplicating things, and it's like, it's okay. I just wanted to reinforce that because I know you're not the only one doing stuff like that, right? Like, I've done that. I do that with the mathematics that I learn. I find, you know, like you got to do it the hard way until you figure out, oh, now I see, and it's really easy. But the first time you see it, it's not. And that's okay. That's normal. What else do we got? Okay, so if we don't have any more questions, let's take a minute and talk about the test format. Does that sound okay? So I'm gonna stop the projection because I'm gonna look at the test so I can look at it as I talk about it so I don't forget about anything. And I certainly don't want to show it to you right now because that kind of defeats the purpose of having, like, you know, a time test setting if you know what it is beforehand. And I need to stop the recording because of the same reason. I don't do the start of a 15 minutes worth of chapter 2. So we'll just kind of start up with chapter 2 here. So chapter 2 is about angles and trigonometry. So we're starting here talking about trigonometry, which is going to be the focus of this first semester. Now, this first chapter of trigonometry is not going to be significantly more than what you saw in your geometry course. So we're going to start with like our basic definitions of sine, cosine, and tangent and all that sort of thing. But before we can even do that, we need to start talking about angles, because sine, cosine, and tangent all operate on an angle measure. So let's start with our first definition. So we're going to start here with a definition. Oh, you can't see anything. Why didn't somebody holler at me? You know, you guys are all too nice and didn't want to interrupt, did you? It's okay. You can interrupt when I'm doing something silly, like talking about things that you can't see. You know? Like, that's important. As I looked up and everybody was writing anything down, I'm like, what's going on? And I looked over and I'm like, oh, that would explain why. So this first definition here, we're looking at a new way or a new unit that we can use to measure an angle. So in your geometry course 2 years ago, primarily you used degrees to measure your angle, right? Which is perfectly reasonable. What we're introducing now is a second way of measuring our angle. And this new unit of measurement, rather than being a degree, is called a radian. So let's draw a little bit of a picture for this situation and talk a little bit about some of the other vocab nested inside of this definition that might need to be rehashed. So when we say central angle, what do we really mean there? So the central angle has to do with a circle. The radius of that central angle is where in the circle, do you suppose? The center, right? So we'd say that angle CAB, remember that when we name angles, we use the vertex as the middle letter, is a central angle. Everybody remember that from geometry now with a little refresher? Okay. And then the other word inside this definition that probably needs some reminder is the word arc. So what is an arc? An arc is just like part of the perimeter for a circle. So CB here is an arc. And remember that when we write the name of an arc, we name it with the endpoints, and then we put an arced hat on it. So we say that the measure then of angle CAB equals 1 radian if and only if the measure of segment, we don't need a measure. We can just say the segment AC is congruent to the arc CB. So this is the same thing as the definition above. We've just written it symbolically rather than in words, but it's equivalent. Is everybody okay there? So we have now two different ways to measure an angle. We have radians and we have degrees. It would be nice to have a conversion to go from one to the other so we can transfer in between the two units. Just like you have feet and you have meters, it's natural to want to have a conversion factor to go translate between the two. That's what we're going to do now, is develop a translation or a conversion factor to go from degrees to radians. And that'll probably be the last thing that we'll do here. So what's going to be most useful is to look at a radius, a diameter for a circle. So that's 180 degrees. And this arc here is 2 pi r. Or, I'm sorry, not 2 pi r. It's half of that, just pi r. Right? Remember that the circumference for a circle is 2 pi r. So for a semicircle, or a half of a circle, it would just be pi r. Again, you may or may not have had that formula at the tip of your head. If you didn't, that's okay. That's why we wrote it down and reminded you guys. After being reminded, I expect that you'll remember it, but if you couldn't remember it without a little reminder, that's okay. So what I can say then is that 180 degrees hold on. Well, I want to say something else first before we do that. So what I want to do here is I want to use the definition of the radian above. Okay? So if the radius is equal to 1, what's going to happen? Okay, let's back up here then. Not clear what I'm asking, that's okay. So I know that an arc measuring 1 radian is cut by a 1 radian angle. Right? That's what we said our definition was, that this is 1 radian if these two things are equal. Right? So by the same assumption then, we know that the measure of the angle CAB is equal to pi radians, since the arc is pi radians. So what our conversion factor becomes is 180 degrees is equivalent to pi radians. So that is our conversion factor that we'll use, and we'll pick up with doing some examples of that next time.